Good evening to everybody. Today we will talk about design patterns in LabView. We will be talking about global variables, local variables, function global variables, and action engines. So these are all design patterns that are used in LabView. Many of those are used in almost any programming language, but you can just after this lecture you will be able to realize what is so specific about using them in LabView. Excuse me that the presentation is in Serbian and I will be speaking in English, but nevertheless you will understand everything. In general, what is the design pattern? So it is like a solution which is really good, and it is like realized by someone, so it can be easily used again and again. So if we have a problem and somebody already proposed the solution to that problem or to that type of problem, it can be considered as a design pattern. What else? By knowing this, you can tell that a design pattern is like a template for programmer. So you can use a template. In general, in life, you can use a template to make your work easier. So you don't have to prepare all the, let's say, outlines each time you perform similar task, but you make an outline once, and then you use that template to provide a solution for your task. The basic concept of a good design pattern is to design code in such a way that you save time, that you improve readability of the code and validity of the code. So in sense of validity in time, so it can last for a lot of time. So even if, let's say, the technology improves and something like that, so we can still use the same solution, the same design pattern. So the main topics about which we have to take care when we are programming in general, but when we are, let's say, designing a design pattern, is scalability, extendability, and reuse of the code. We will just extend this set of features. So the first one, the first feature, which will, let's say, provide us an application which is designed in a good way, is scalability, and that means that it is easier to add a new component in our particular solution. So if we need to, let's say, extend our solution, we can use some component that has been already developed. Modularity. So when we are talking about feature of modularity, we have to know that sometimes we have to make smaller modules out of bigger modules in order maybe in some other project to use that smaller modules. So if we make, let's say, a solution which can be considered as a black box, and we don't know exactly what is happening inside of that black box, but for some other project we need just a part of that solution. So we have, let's say, to make some modules out of the big solution, and those modules can be used afterwards in some other tasks. Reusability, of course, it means that we can use the same code, the same, let's say, template in some other or some future projects. Extendability is that if you have like a particular, let's say, solution, that you can provide another functionality to that solution. So in that case, you can improve your solution. And simplicity is the way how to program in the most simple way and to provide the best solution. So it is a kind of compromise. So usually the best solutions are the most simple ones. But one has to take care if that simple solution, that simple code can provide a solution for our problem. When we say simple, we mean it should be readable, relatively easy. It shouldn't use too much resources of our computer, so computing power, memory, and so on and so on. So the solution in some way have to be optimized. So if we want to make, let's say, a division of all design patterns, not all, but some design patterns that are used on LabView, we can divide them as following in this slide. So functional global variables, state machines or state charts, event-driven user interfaces, producer-consumer patterns, and queued state machine with producer-consumer patterns. So these are only some of them, and we will go through most of them in this course. So you will see about each of them in some specific lectures. Okay, in order to realize the design patterns and everything that comes out of design patterns, maybe you first should realize and understand something about, let's say, way how we treat communication between particular instances in LabView. So to communicate, we can use many different things. So some design patterns, but the most simple things that can be used for communication within LabView code are, for example, local variables. So they are used if somebody wants to read or write from controls or indicators within one VI. And usually they are useful when you want to communicate between loops within one VI. On the other hand, global variables are used when you want to, let's say, transfer data from one VI to the other. And particular thing for global variable is that it is like a type of VI that possesses its front panel but does not have a block diagram for that front panel. So these are mostly the characteristics of both types of these variables. So both of them should be initialized, and so in order to read from them, you first must write to them something, some initial value. If they're not initialized, they contain the default value for that particular data type they are made for. And what is the, let's say, the drawback of using these variables is that every copy of this variable just takes up a new memory slot. So if you have, let's say, 10 local variables that, let's say, refer to the same real physical variable, they will take up to 10 memory slots for that data type that corresponds to that variable. So we would just accumulate that. So it's not like a reference to the memory slot, but we are making every time a new copy of the memory slot. And with this, we can have like a problem with the race condition. You know what the race condition is. The problem with the race condition is when you can't tell every time the exact order of execution of some commands in your code, and depending on what is, let's say, the order of execution, the different output will become, okay, will happen. Both of these are not able to follow, let's say, data flow of the error, and they are constrained that they can't do some let's say, specific tasks with data. So, for example, if you want to stop the parallel loop, this would be the first example. So, I'm not sure if everybody can see it. It's a little, let's say, bad here. How is it done? Okay. So, let me just. These are two parallel loops, and we are trying to stop them by pressing only one button. So this button stop. If it's pressed, the true constant is moved to this conditional loop terminal, and it's not really easy to see here, but there is a wire here, and that wire is transferred to the loop conditional of this second loop, and really what is happening here. So at the point we press the stop button, the stop element goes to this loop conditional, it stops this loop, and then afterwards, because there is a branch here, that stop value is transferred here, okay, and it should go in here, okay, and afterwards, after this is completely done, the second loop has stop value here, and then this button, this wire is transferring here to this loop condition, and the second loop is stopped. So what is exactly the problem here? So this is, in this way we cannot provide like a parallel stopping of the loops, because what will happen until this button is pressed here? So this loop will just go, and so for example, if we provide here to this loop to work for 70 seconds, it will make 70 iterations, and then we stop it, okay, then this terminal provides true constant, and it goes here, and while this loop has performed 70 iterations, this has performed none. And then afterwards you stop, this performs only one, and that's it. So this one has done much more work than this one, so it's not really parallel work. On the other hand, what is happening here? If we use a local variable, so in here it is a local variable. So if we stop this, and if this loop has done like I don't know 30 iterations, and while doing those 30 iterations, this value is false. This copy of that value, so local variable, the copy in the memory of that value will be also false. But when this comes to be true, the copy also comes to be true, and both loops are stopped, so they have performed the same number of iterations. Also, the same issue is with global variables, but you can use them, for example, in different VIs. So usually we use them in different VIs. So about race condition, so we can, let's say, imagine a race condition when, let's say, two or more threads or processes can reach to some part of code, and I guess the execution of the code is different depending on which thread has reached that part of the code first. So the first thread reached the part of the code, the output would be different than the case when the second thread reached that part of the code. But if you know all the expected outputs and they won't provide any issues, then the race condition is not such a big problem. But usually it is, because the race condition usually refers to some errors of synchronization, and then it's a problem because few processes cannot interact in the way they should, and then they bother one another. So maybe we have to provide some output from the first process to be, like, let's say, an input to the second one, and so on and so on. And if we cannot, let's say which process will reach that part of the code that is important to perform the action, and for example, the second one reaches that. In that case, we will not have like the provided output from the first one that is input to the second one, because we firstly the second process firstly reached the wanted code. So usually race condition leaves the program in undefined state, and by programming in this way, like LabView works in data flow programming, it is much easier to resolve these race condition problems. And of course, when you have parallel loops, that is usually the case even in LabView when a race condition exists or shows up. So if you have only one loop, you can provide data flow for all elements, and race condition won't happen. But when you have parallel loop, then you also have to consider what will happen in the case of race condition. So FG V's are really useful design patterns that are usually used to resolve problems like race conditions, and in its basics, function global variable present VI that uses a loop with uninitialized shift registers in order to save global data. So it means when you use a simple, let's say, while loop with uninitialized shift register, it means each time when you call that loop from some, let's say, other VI that is upper VI to those to that which is called. So when the loop iterates, the product of the action within the loop will be saved in the initialized shift register and prepared for the next call of that VI. So the data is saved even when VI is not executed, and it is always there until it is, let's say, drawn back from the memory. And what are the pros of this approach? So FGVs don't make copies in memory slots, memory locations. They are used in general to resolve problems with race conditions, they can really easily, let's say, follow the data flow of error signals, because you can easily integrate error signals within functional global variables, like use it like simple error signal within the loop, and they can use all other like activities when compared to simple local global variables, not just reading and writing. So you can design an action what function global variable should do. And what is also really nice, we can let's say call these functional global variables from many VIs, like directly from as many we can. So in order to create this FGV, we have to know about while loops, shift registers, and the fact that non-initialized shift registers have memory, key structures, enumerated controls, and sub-VIs. So I've been talking earlier about enumerated controls and about sub-VIs, so you're already familiar with this. I won't go much into this. So enumerated controls means that you make a simple custom control which has like enum control within itself, and you define let's say a states of that control. So that control will be used to tell to our code exactly to which state it will go to. And sub-VI, it is like regular VI, as you know, and it can be called up from some other VI. We have just to, let's say, mark the terminals which should be inputted out, the terminals, and so on and so on. So we will just go now through some basic, let's say, actions or mechanisms of functional global variable. So usually, when you write function in any or method in any programming language, you have to have like a set and get also send get methods for the object that is defined. And in here also, for this particular functional global variable, you usually have to have set and get object, not for only for this one in particular, but for any. It is like unwritten rule. And then you will and you need then to have an action. So what will happen in case something happens that needs to be let's say saved or triggered or counted or something like that. So this is the action. So some particular piece of code that is different from simple read and write, but that performs some action that this functional global variable is really intended. These are some more major characteristics of FGV. Is that this enumerator, so the enumerated control, it chooses the action, so the mechanism. So if we are going to use get, set, or action, let's say mechanism, functional global variable saves the results in non-initialized shift register, and the general rule is that the loop only executes only once. So, for example, if you want to make like a simple counter, for that particular case, you will have these actions. Let's say, so these actions are like can be understood as functions. So initialized or methods: initialize method, read method, increment method, and decrement method. Initialized method will just like set the default value. So the default value will be the default value for the particular data type it is used in this functional global variable. Read means just read the current value of the variable it is used in this functional global variable. Increment, so let's just increment the number of the in the variable. So usually when we say increment or decrement, we are thinking about integer values, so we cannot increment and decrement some double values or something like that. And this example is really obvious because all these let's say wires and controls and indicators are blue, so it means they are integer, and even in here it says it's integer 32. So and there are these functions, so they are contained within this case. So in here it is initialized, so a constant for initial value. Read just reads the current value. Increments when this FGV is called up, it increments the value of this data type for 1, and of this variable of integer data type for 1, and decrement means it will just decrement for 1 the value of the variable of integer data type in here. So this is like a simple counter. So if you want to count something, we will use this functional global variable with these actions or methods. So like a special type of FGV is action engine, and this let's say design pattern once again has to provide the following. So to identify the critical part of the code, to determine the actions which enable modification of that part of code, and to let's say install and encapsulate get, modify, set methods within one FGV. So and as general FGV action engine also saves data from one call of action engine to the other. So basic characteristics are the same like for FGV. So it contains a loop with non-initialized shift register. The loop executes in only one iteration, and so there are a couple of ways how to implement the action engine via loops. So the first one is via while loop. So you can see it has like initialized registers over here, input and output register, and in here true constant is wired to this loop conditional, so this enables the loop to execute only once. Similar to that, you can see this for loop approach. So this part is the same, but the only difference is that we don't have a loop conditional like here, but we provide the exact number of execution of iteration of this loop here. Okay, so yeah, there are different implementation of action engine apart from these ones. So it can be let's say implemented via feedback node. So then of course in this particular case for here we don't have to use, let's say, need to use a specific loop, so while or for, but to use only a feedback node. And so what happens here in here, for each iteration of this upper loop, all value is provided, so the action is let's say programmed here. After the action is performed, the output, so the new value is provided here, and what the feedback node does, so it takes the new value and that new value is transferred upstream to the feedback node, and afterwards for the next iteration this downstream
will provide that new value to be ready for the next iteration as an old value, and so on and so on and so on. So the concept is the same. There are, like, let's say, two examples how this is working. So pretty much these examples are similar. It depends where you want to place this feedback node. So this particular example shows that the indicator displays the value placed on the feedback node. So this value here, so this new value that will be provided for the next iteration as an old value will be placed to this indicator. In this particular case, this indicator is after feedback node, so it means that it will show the old value in the next iteration, not the new in the current iteration. But it is just like play with code. So this way of implementing action engine via feedback node is efficient from several reasons. So feedback node is, like, particularly designed in order to provide functionality that action engine should possess. It somehow makes the readability of the code much easier, and of course it is easier to create it than single loop with one iteration shift register. So you have to only include one object feedback node, and that's it. You don't have to place shift register at the beginning, at the end, and to place the loop and put let's say true constitute to the loop terminal, conditional terminal, and so on and so on and so on. So, for example, for action engine example, this is a counter that we already discussed with while loop, and so in here you have, like, the things that we would call actions are methods over here. So the same methods. This one is called get. This one is called reset. Over there in the previous example we call this initialize, but it is pretty much the same. This one is called increment. The function is the same, so it just increments the counter, and increment, it just increments the counter. This comment here provides us with the knowing, so which of these methods should be performed. So we're at this point at command. Sorry, at command we have get value, and then we will perform get value method. And if we have reset value, we will perform reset method, and so on and so on. Furthermore, if we want to do the same, but for example, like this with value loop, so it would look like this, and for loop it would look like this. So here only one method is shown, so get value for while loop and increment for loop. And we were telling that it's easier than to track error signals. So if you can see, it can be done really simple in this way. We just need another case that contains all the code, and we provide to that case error control at the input, and error indicator and the output, and just let's say wire an error through it. So in this way we can provide let's say data flow of error handling throughout our entire code. And of course it should be made as sub VI, and that sub VI when it is used in some other VI would look like this. So these would be, let's see, the inputs, and this would be the output. So the comment, the current value of the counter. So these are, let's see, the main ones, and these two provide the taking care of error handling. And we will show here one more example. It is an example of timer. We will use even state variables here, and this example is really useful because we will use it in many examples afterwards in coding, and it is useful because in general timers are things that are really necessary for programming anything that has to be done, let's say, in real time, and even not only in real time. So usually for any reasonable code, we will have some timers, so we will have to wait for a particular number of seconds for something to happen, or milliseconds, or we will have to trigger something after some amount of time or something like that. So there are many things and many usings of timers. So this approach via state variables is used when we want methods of Action Engine to completely, let's say, remove from the mechanism of data storing from shift registers, and in this way we let's say make it easier to track the changing in code or something like that. We don't have to take care about data storing because it is done at the first instance, and we don't have to care about it, so we can change only the functionality itself. So we can provide as many functions for this particular Action Engine we want. Usually for timer we don't need many, but we can provide as many as we want, and not taking care anything about data storing. And so these state variables are exactly the things that we are saving from one iteration to the other, and within this approach, these methods for which we said that it can be as many as we want are defined within a piece of code that is also a VI, but it is called kernel VI. And so these state variables represents the inputs to these kernels, and afterwards the kernel does what is intended to do, some action, some functionality, and it provides the new values of state variables to the output. And what is the job of Action Engine? So its job is to store that data until the next call of Action Engine. So this is like general procedure. We have to define a set of functions that will that Action Engine will do. So this represents the actions or the methods of Action Engine. We have to design an algorithm for every method, so code what it has to do. So we have to implement this code for each method. Of course, we have to identify what are the state variables, so what has to be stored for the next iteration. So from one iteration to the other, it's really important to identify state variables at in the right way. Then we have to make the kernel, and so the kernel, as it is said here, represents sub-VI with key structure and enum control at the input of the key structure, and that enum control consists all the actions that are needed for Action Engine. Of course, each method is implemented in a particular case, and what is really necessary to do is to make input and output terminals for all state variables. And of course, we have to make sub-VI, which provides storing of state variables and their manipulation via kernel. And the fact is that this sub-VI is in fact action engine. So I'm not sure how much can you see here. So we will talk about more about this more in exercises, but these are the methods of timer. So the first method is, let's say, elapsed time. The second method is reset. There are two state variables. The one is timestamp, the other one is elapsed time. So we have like state variable made as cluster, which consists of all state variables that are needed for this action engine to work. In this particular case, it is timestamp, so the current timestamp, and the elapsed time, so the time that has passed from some instance of time before. So how this function works, elapsed time, so it takes up the system time, and it is, let's say, placed as a new time to the next iteration, as a new time step for the next iteration. But what does this elapsed time, how does it work? So it takes the current timestamp and it just takes out so the earlier timestamp from the previous iteration is taken from the current timestamp, that is the delta time, so the time that has passed between two calls of this action engine, and elapsed time, so the time of the timer, so it might be 2 seconds, is then added to that delta time, so it might be like 1 second that has passed from the previous call, and that is added here, and the new elapsed time is 3 seconds. So if the previous elapsed time was 2 seconds and the pass time between two calls of this function is 1 second, the new elapsed time will be 3 seconds. This function reset is even simpler. So the new timestamp will be the timestamp taken from this particular call, system time from this particular call of action engine, and elapsed time, it will be 0. So because we want to reset the timer, so we will reset it to 0. And what we do next, so we define this as kernel of the timer. So this is the input, this is the input, this is the output, this is the output of the kernel, and we can now see the action engine. So the one input, the other input, so the state variable, first output, the other output, state variable, and because we want to store the values of the state variables, they are put to these shift registers. And this is the implementation via while loop, this is the implementation via for loop, and this is the implementation via feedback node. And we will talk much more about these in exercises. We will do many examples with this, and you will see why they are so good. Because, for example, if you are using this one, the approach in here, you can take care about everything in your code at each instance. So when this is realized, nothing has to stall. For example, we don't need to wait for some default timer to count or something like that. So you will see this from the examples. Thanks. That's it for today. Thank you.